Good day, everybody. How are you all doing? Today we are going to talk about the second part of entropy lecture. So here I go. Air initially at 17 degrees Celsius is compressed in an isentropic process through a pressure ratio of 8.1. Find the final temperature assuming constant specific heats and variable specific heats and using EES. Okay. So constant specific heat, the formula is this T2 divided by T1 with entropy constant S is equal to constant is equal to P2 by P1 raised to the power of K minus 1 by K. For air, K is 1.4 and a pressure ratio of 8:1 means P2 by P1 is equal to 8. So T2 is equal to T1 times P2 divided by P1 uh, raised to the power of K minus 1 by K. And so T2 becomes 252.3 Celsius. Variable specific heat method is P2 over P1 is equal to P2 by P reference divided by P1 by P reference is equal to P reference 2 divided by P reference 1. And uh, so PR2 is equal to PR1 times P2 by P1. Then you substitute uh, P2 by P1 is equal to 8 and PR1 is 1.231 because we are using air data from table A17. Finally, we get temperature as 522.4 Kelvin or 249.4 Celsius. Okay, a second variable specific heat method. So we have T1 is this, and then we look at the air temperature to get the entropy at T1. And for isentropic process, S20 is equal to S10 plus R times natural logarithm of P2 divided by P1. Okay, plug in the values, substitute the values, and get S20 as 2.26482 kilojoule per kilogram Kelvin. Okay. And ES is the software, so we are not going to. Then there is another problem. Okay. So part A is air initially at zero point 0.1 megapascal, 27 degrees Celsius, is compressed reversibly to a final state. Find the entropy change of the air when the final state is zero point 0.5 megapascal and 227 degrees Celsius. Part B, entropy change when the final state is zero point 0.5 megapascal, different temperature, 180 degrees Celsius, and find the temperature at zero point 0.5 megapascal that makes the entropy change zero. Assume air is an ideal gas with constant specific heats. So S2 minus S1 is equal to Cp, and it's a reversible process times ln over T2 minus divided by T1 minus R ln of natural logarithm P2 by P1. Substitute the values. S2 comes out as 0.0507 kilojoule per kilogram Kelvin. For the second part, same idea, but S2 comes out as negative, okay, 0.0484 kilojoule per kilogram Kelvin. Okay, and so forth. Okay, nitrogen expands isentropically in a piston cylinder device from a temperature of 500 Kelvin while its volume doubles. What is the final uh, temperature of nitrogen and how much work did the nitrogen do against the piston in kilojoule per kilogram? Okay, so S is constant in the path and it's going from P1 to P2. Okay, so isoentropic expression because entropy is constant. We use the second law, T2 is equal to T1, specific volume 1 divided by specific volume 2, raised to the power of K minus 1. And assuming constant properties, the temperatures are related by this formula. So we find T2 Note for isentropic process, reversible adiabatic, the heat transfer is zero. The conservation of entropy for this closed system becomes E in minus E out is equal to delta E. And we know minus W is equal to delta U, or W is equal to minus delta U. Using ideal gas relation per unit mass, work per unit mass is W is equal to minus mcv T2 minus T1, that's a total work. So specific work unit mass is W divided by M is minus CV T2 minus T1. Substitute the values and the work is positive. For the isentropic process, PV raised to the power of K is constant. Use the definition of boundary work to show that you get the same results as the last example. So let's do the next problem. Carnot engine has 1 kilogram of air as the working fluid. Heat is supplied to the air at 800 Kelvin and rejected by the air at 300 Kelvin. At the beginning of the heat addition process, the pressure is 0.8 megapascal, and during heat addition, the volume triples. Calculate the net cycle work, part A, assuming air is an ideal gas with constant specific heats. Part B, calculate the amount of work done in the isentropic expansion process. And part C, calculate the entropy change during the heat rejection process. Okay. Proper relation, ideal gas equation, constant pressure, air system boundary inside the piston cylinder process, and process and process diagram. So you're going from 1 to 2, 2 to QH is the heat coming in, 2 to 3, 3 to 4, and back to 4 to 1. Okay. And 1 is a temperature high, hot, and TL is temperature low. You get heat at QH, at TH, and you lose heat at QL, at TL. So applying the first law, closed system to the constant temperature heat addition process, Q net 1, 2 minus W net 1, 2 is delta U 1, 2, which is MCV T2 minus T1, which is equal to 0. So Q net 1, 2 is equal to W net 1, 2. So for ideal gas isothermal process, W net 1, 2 is W other 1, 2 plus WB 1, 2. And that is 1 to 2 pressure, integration pressure dV. So it's MRT is a constant ln of V2 by V1. Substitute the values and you get 252.2 kilojoule. Okay, so QH is equal to 252.2 kilojoule. Cycle efficiency is zeta thermal, W net cycle divided by QH. For Carnot cycle, the efficiency is also given by eta thermal is 1 minus TL by TH, 0.625. Okay, net work done by the cylinder is given. Okay, and then we apply the first law. Apply the part B, apply the first law closed system to the isentropic process 2 to 3. But the isentropic process is adiabatic reversible, so Q23 is 0. So E in minus E out is delta E, and minus W is equal to minus delta U. So W23 is minus MCV T3 minus T2, and you get W23 as 359 kilojoule. This is the work leaving the cycle in process 2 to 3. So then we calculate delta S3 to change in entropy from process 3 to 4. Use this equation, but T4 equal to T3 equal to TL is 300 Kelvin, and we need to find P4 and P3. Consider process 1 to 2. T1 equal to T2 is equal to TH, 800 Kelvin. So for ideal gases, M1 is equal to M2. And this is the ideal gas relationship. And therefore, we can calculate P2. And then you plug the substitute the P2 value to get P3. Once you get P3, you can also calculate P4 using the same type of relationship. P4 is equal to P1 is T4 by T1 in parenthesis raised to the power of K divided by K minus 1. And hence you can calculate delta S from this formula, which is minus M times R universal gas constant multiplied by natural logarithm of P4 by P3. 3. Substitute the value delta S is minus 0.315 kilojoule per Kelvin. Okay. So they have another problem in which air at 100 kilopascal, 25 degrees Celsius enters a steady flow compressor with a mass flow rate of 1.5 kilogram per second. The air is compressed to 500 kilopascal, 450 Kelvin, while the work input is 670 kilowatt. Okay. The surroundings to the compressor are at 25 degrees Celsius. Assuming constant specific heats at 300 Kelvin, is this process possible? So, consider a turbine, pump, compressor, or other steady flow control volume work producing device. General law for steady control volume is En is equal to E out, mass rate or energy rate coming in is equal to energy rate going out. The dot means rate. Q dot net plus, so E dot in can be written as Q dot net plus sum of uh, mass flow rate times enthalpy plus kinetic energy plus potential energy. On the outside, on the other side, the E dot out is W dot net plus exiting mass times again enthalpy, kinetic energy and potential energy. For a one entrance, one exit device undergoing an internally reversible process, this general equation of the conservation of the energy reduces to, on a unit mass basis, delta W reversible is equal to delta Q reversible minus dH minus dKe minus dPe. All these are changes. Changes in enthalpy, changes in kinetic energy, change in potential energy. But delta Q reversible is TDS. So delta Q, instead of delta Q reversible, we write TDS. T is the temperature, absolute temperature. DS is the change in enthalpy, minus change in enthalpy, minus change in kinetic energy, minus change in potential energy. Okay. So delta W reversible is minus VTP, minus DKE, minus DPE. Integrating over the process, we get W reversible is minus integration from 1 to 2 state VdP minus delta K minus delta P kilojoule per kilogram. Neglecting changes in kinetic and potential energies, reversible work becomes W reversible is minus integration from 1 to 2 VdP. Based on classical sign convention, this is the work done by the control volume. When work is done on the control volume, such as compressors or pumps, the reversible work going into the control volume is given by this. W reversible M is integration from 1 to 2 VdP plus delta kinetic energy plus delta potential energy. Delta means change in kinetic energy, change in potential energy. And the units are kilojoule per kilogram. Since the fluid pressure drops as the fluid flows to the turbine, dP is less than 0 and the specific volume is always greater than 0. So W reversible turbine is greater than 0. To perform the integration, the pressure volume relationship must be known for the process. Since the fluid pressure rises in compression and pump, as the fluid passes to the compressor or pump, dP is greater than 0. Specific volume is always greater than 0. W reversible is also greater than 0 coming in, or work is supplied to the compressor or pump. To perform the integral, the pressure volume relation must be known for the process. The term compressor is usually applied to the compression of a gas. The term pump is usually applied when increasing the pressure of a liquid. Pumping an incompressible liquid for an incompressible liquid, the specific volume is approximately constant, taking V approximately equal to V1, the specific volume of the liquid entering the pump. The work can be expressed as by this expression. For steady flow of an incompressible fluid through a device that involves no work interaction, such as nozzles or pipe or a pipe section, the work term is 0, and the equation above can be expressed as the well-known Bernoulli equation in fluid mechanics. V times P2 minus P1 plus delta Ke, change in kinetic energy plus change in potential energy is equal to 0. So, is an okay extra assignment, okay. Saturated liquid water at 10 kilopascal leaves the condenser of a steam power plant and is pumped through a boiler pressure of 5 megapascal. Calculate the work for an isentropic pumping process. So work for the above analysis, from the above analysis, the for the reversible process can be applied to isentropic process. It is left for the student to show this is true as W dot compression is equal to M dot V. M dot means change in mass flow rate times, or change of mass flow rate with time, times V1 multiplied by P2 minus P1. Here at 10 kilopascal, V2 is equal to V1 equal to 0.001010 meter cube per kilogram, and WC is work per unit mass is capital W dot C divided by M dot, okay, is equal to V1, that's a specific volume, times P2 minus P1. So we substitute the value. So work per unit mass WC is 5.04 kilojoule per kilogram. Okay, so we basically get minus 0 minus 2 minus it will make it positive. W dot C is equal to M dot H2 minus H1. So we need information. So we need to go to the tables. Okay. To get H2 and H1, and then we'll plug it in the equation. So WC workflow per unit mass is W dot C plus divided by M dot is H2 minus H1. Okay. So mass steady flow devices operate under adiabatic conditions, and the ideal process for the devices is the isentropic process. The parameter that describes how device approximates a corresponding isentropic device is called the isentropic or adiabatic efficiency. It is defined for turbines, compressors, and nozzles as follows. Okay. So turbine is shown over here. Okay, it's irreversible. Pressure, temperature, one coming out, P2 going out. Okay, and actual is irreversible. Ideal is reversible. Okay, and they show it in the enthalpy H and S diagram at two different pressure. So you have the isentropic process, the straight vertical line going down, red line. That's the isentropic, that's the ideal process. The actual process will deviate from the straight vertical line going down. The isentropic process is the maximum possible work output that the adiabatic turbine can produce. Therefore, the actual work is less than the isentropic work. Since efficiencies are defined to be less than 1, the turbine isentropic efficiency is defined as you get H1 minus H2A divided by H1 minus H2S. Well-designed large turbines may have isentropic efficiencies above 90%. Small turbines may have isentropic efficiencies below 70%. The isentropic work compressor and pump. The isentropic process is the minimum possible work that the adiabatic compressor requires. Therefore, actual work is greater than the isentropic work. Since efficiencies are defined to be less than 1, the compressor isentropic efficiency is defined as, they're showing you the process, WC going in, T1, P1, okay, and leaving, okay, compressor or pump. And you see the ideal process, isentropic process is the vertical line going up from P1 to P2. Actual process deviates from the ideal process, as you can think, well imagine. And finally, eta C compressor efficiency is given by this formula. Well-designed compressors have isentropic efficiencies in the range from 75 to 85%. Okay. Same idea with nozzle. The isentropic kinetic energy at the nozzle is the maximum possible kinetic energy at the nozzle exit. Therefore, the actual kinetic energy at the nozzle exit is less than the isentropic value. Since efficiencies are defined to be less than 1, the nozzle isentropic process is efficiency is defined as given in the bottom. Again, isentropic process is the vertical line going down. The actual process deviates from that. And we can calculate the efficiency is actual kinetic energy at the nozzle exit divided by uh, isentropic kinetic energy at nozzle exit, which is V2A square, velocity square divided by 2. You're taking the kinetic energy. A means actual, S means isentropic process. For steady flow, no work, neglecting potential energy and neglecting the inlet kinetic energy, the conservation of energy for the nozzle is H1 is equal to H2 adiabatic plus V2A square divided by 2. The nozzle efficiency is written as this, H1 minus H2 adiabatic divided by H1 minus H2S. That's the isentropic process. That is the theoretical process. Isentropic work for the turbine in example 7.6 is 1152.2 kilojoule per kilogram. If the isotropic efficiency of the turbine is 90%, calculate the actual work. Find the actual turbine exit temperature and quality of the steam. So, adiabatic WA is eta turbine, that's the adiabatic one, times WS. And we know those things, so we multiply, so we get W adiabatic, okay? And we also know eta of the turbine is given by this H1 minus H2A adiabatic, or actual, I meant to say actual, divided by H1 minus H2S. So WA is the work done actually, okay? Actually turbine work, okay? Now need to find the actual exit state for the team. From example 7.6, steam enters the turbine at 1 megapascal, 600 degrees Celsius, and expands to 0.01 megapascal. And you know P1, T1 from the table, you know H1, S1. At the end of the expansion process, P2 is this, and S2 entropic is equal to S ideal is equal to 8.03, from which we can get H2A and X2S. Okay, the actual work is WA H1 minus H2A. So H2A is equal to H1 minus WA is 2660.9 kilojoule per kilogram. Okay, second, okay, we will not go into this. This is a compressor. Air enters a compressor and is compressed adiabatically from 0.1 megapascal, 27 degrees Celsius, to a final state of 0.5 megapascal. Okay, so it's compressed from 1.1 megapascal to 0.5 megapascal. Find that work done on the air for a compressor, isentropic efficiency of 80%. So here is the picture, property relation, conservation principles for the isentropic process. Q net is 0, assuming steady state, steady flow, and neglecting changes in the kinetic and potential energy for one entrance, one exit. The first law is this. E dot in is equal to E dot out, or dot means flow rate, is M1 dot H1 plus W dot CS is equal to M2 dot H2S. Conservation of mass gives M1 dot is equal to M2 dot is equal to M dot. So finally, WCS dot is equal to M dot times H2S minus H1. So H2S is the ideal for the isentropic process. And so WCS specific work is given by W dot CS divided by M dot is H2S minus H1. And isentropic work is given by Cp T2S minus T1. So we need to find T2S using the relation is 475.4. Conservation of energy becomes WCS is equal to Cp times T2 minus T1, plug in the values, substitute the values. WCS compressor is 176 kilojoule per kilogram. And we know WC, the efficiency for the compressor is WS by WA, or WCA is equal to WCS by eta of the compressor. So WC is 220 kilojoule per kilogram. There's another problem, and let's see. So this is nitrogen expands in a nozzle from a temperature of 500 Kelvin while its pressure decreases by factor of 2. What is the exit velocity of nitrogen when the nozzle isentropic efficiency is 95%? Nozzle control volume, property relation, we need ideal gas equation assuming specific heat, and process diagram. First assume an isentropic process and then apply the nozzle isentropic efficiency to find the actual exit velocity. So conservation principle for the isentropic process, Q net is 0, assume steady state, steady flow, and no work is done. Neglect the inlet kinetic energy and changes in the potential energies. Then for one entrance, one exit, the first law reduces to E dot M is equal to E dot out. And plug the relationships from which the conservation energy reduces to V2S is equal to square root of 2 times H2 minus H1. Okay. And basically for H we can write CPT1 minus CP2S. Okay. So V2S is equal to square root of 2 CP times T1 minus T2S. Now we just plug in the values. First we get T2S, then we plug in the value to get the V2S, from which we will calculate eta of the nozzle. Actually, using that, because eta of the nozzle is given to us, we can calculate V2A, the actual velocity. Okay. The principle of increase of energy for any system is expressed as an entropy balance by this: total entropy increasing minus total entropy leaving minus total entropy generated is equal to change in total entropy. So S in plus minus S out plus S generated is equal to delta S, or change in entropy of the system. The entropy balance relation can be stated as the entropy change of a system during a process is equal to net entropy transfer to the system boundaries and the entropy generated within the system as a result of irreversibilities. So entropy change is equal to entropy at the final state minus entropy at the initial state at S2 minus N1. Mechanism of entropy transfer S in and S out. Entropy can be transferred to or from a system by two mechanisms: heat transfer and mass flow. Energy transfer occurs at the system boundary as it crosses the boundary, and it represents the inner entropy gained or lost by a system during the process. The only form of entropy interaction associated with a closed system is heat transfer, and thus the entropy transfer for an adiabatic closed system is 0. Heat transfer, the ratio of the heat transfer Q at a location to the absolute temperature T at that location is called the entropy flow or entropy transfer, and is given as S heat is equal to, going from state 1 to state 2, integration delta Q over T, or summation, which is almost equal to summation of Qk divided by Tk. Work is entropy free and no entropy is transferred by work. Energy is transferred by both work and heat, whereas entropy is transferred by heat and mass. Entropy transfer by work is 0. Okay. Mass contains entropy as well as energy, and entropy and energy contents of a system are proportional to the mass. When a mass in the amount m enters or leaves a system, entropy in the amount of ms enters or leaves, and where S is the specific entropy of the mass. So entropy transfer by mass, the S mass is M times S. Okay. Entropy generation, irreversibility such as friction, mixing, chemical reaction, heat transfer through a finite temperature difference, unrestricted expansion, non-quasi-equilibrium expansion, or compression always cause entropy of a system to increase, and entropy generation is a measure of the entropy created by such effects during a process. So entropy balance for any system undergoing any process can be expressed in general form as S in minus eta S out, which is net entropy transfer by heat and mass plus S generated. Entropy generation is equal to change in entropy, and the units are kilojoule per kilogram, per Kelvin. The entropy balance for a system undergoing any process can be expressed in the general form as same thing, rate of net entropy transfer, rate of net entropy transfer by heat and mass plus rate of entropy generation is equal to rate of change of entropy, and units can be kilowatt per Kelvin, where the rates of entropy transfer by heat transfer at rate q dot and mass flowing at the rate of m dot are s dot heat is equal to q dot by heat and s dot mass is equal to m dot s. The term S generated is the entropy generation within the system boundary only, and no entropy generation that may occur, and note that entropy generation that may occur outside the system boundary during the process as a result of external irreversibilities is gen equal to 0 for the internally reversible process, but not necessarily 0 for irreversibilities. Okay. The total entropy generated during any process is obtained by applying the entropy balance to an isolated system that contains the system itself and its immediate surrounding. Okay. And you got the picture. S in through mass and then heat, S out, mass and heat, and entropy of the system. Entropy generated is greater or equal to 0. That means irreversibilities are there. So taking a positive direction of heat transfer to the system to be positive, the general entropy balance for the closed system is delta Q, summation of Qk by Tk plus S gas is equal to delta S system is S2 minus S1. For an adiabatic process, Q is 0. Adiabatic closed system S generated is equal to delta S, change in entropy of the adiabatic system. A general closed system and its surrounding isolated system can be treated as an adiabatic system, and the entropy balance become system plus surrounding S generated is equal to change in entropy, sum of change in entropy, which is change in entropy of the system, change in entropy of the surrounding. The entropy balance for control volumes differs for closed system in that entropy exchange due to the mass flow must be included. Okay, the bottom line is for a general steady flow process by setting delta S, CV is the control volume is 0. The entropy balance simplifies to S dot generated is equal to M dot entrance with S entrance multiplied by S entrance minus M dot leaving and S leaving minus Q dot K minus TK. For a single stream, one inlet, one exit steady flow device, entropy balance becomes S dot generated is equal to M dot SC minus AC, SL, SI, entry minus leaving, minus sum of Q dot K divided by T, absolute temperature K. Okay. So S generated is M dot AC by minus SI. Okay. This states that the specific entropy of the fluid must increase as it flows through an adiabatic device since S dot generated is greater or equal to 0. If the flow through the device is reversible and adiabatic, then the entropy will remain constant regardless of the changes in other properties. Therefore, for steady flow, single stream, adiabatic reversible process, S entering is equal to S leaving. Okay. So an inventor claims to have developed water mixing device at which 10 kilojoule kilogram per second of water 25 degrees Celsius, zero point 0.1 megapascal, zero point 0.5 kilojoule kilogram per second of water 100 degrees centigrade, 0.1 megapascal are mixed to produce 10.5 kilograms per second of water as a saturated liquid at zero point 0.1 megapascal. If the surroundings of this device are at 20 degrees Celsius, is this process possible? If not, what temperature the surroundings? Okay, so basically you do uh, process, you do a diagram, okay, and then you do energy balance and apply the first law and show that Q dot net must be transferred from the surrounding to this giving for the process to be possible. Second law must be satisfied, okay, and this is the second law. Okay, for steady flow, delta S reverse is equal to 0, control volume is 0. Solving, we get since S dot generate must be greater or equal to 0 to satisfy second law, this process is impossible and the inventor's claim is false. Okay. And one way to think about this process, okay. Process as follows. Heat is transformed the surroundings at 315.75 Kelvin in the amount of 1997.7 kilojoule per second to increase the water temperature to approximately 42.75 Celsius before the water is mixed with the superheated steam. Recall that the surrounding must be at the temperature greater than the water for the heat transfer to take place from the surroundings to the water. Okay, and this is the final table. So this is a problem we can do. So I'll stop here today. If you have any question or comment, please write me a note. If you like this video, please give me a thumbs up. I really appreciate that. And it motivates me to produce more interesting videos just for you. And if you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button. And also please click on the bell because that will help you in the sense you will be notified every time I upload an new video. So please click on the bell too. And please subscribe to my channel by hitting the red subscribe button. And please do not forget to watch me tomorrow when I'll be back with another interesting video. Thanks for taking the time to watch my video. I appreciate that. And I hope to see you tomorrow. Take care. Have a nice day.